Okay, the last lesson of the solids units is about spheres and hemispheres. So a sphere is a ball. It is a non-polyhedral. That means it does not, a polyhedron had polygons and edges and faces and vertices, so it does not have that. So it's a non-polyhedral solid. It is defined as the set of all points in space. All right, so here's what makes a sphere different from a circle. That are a given distance from a given point called the center. A sphere has no base, it has no faces, it has no edges, and it has no vertices. Okay, it does have a center and a radius. So any point on a sphere, right, is the same distance from that radius. So that's equidistant to the point on this part of the sphere, and maybe the sphere goes back here, and it would be equidistant back there. All right, imagining that that's 3D. Okay, that's getting too complicated. But anyway, so the radius will touch, if you reach out from the center, the edge of the radius will touch any part of the sphere. So this is the center. Right here. And then the radius is right here. All right, so a little bit of definitions and labeling for a sphere. All right. Remember that the radius is half of the diameter. So just a nice reminder about not forgetting that you might be given the diameter and not just the radius. All right, let's take a look at the definition of a hemisphere. And for good measure, we'll switch colors. It is one of two congruent halves of a sphere. So it's a sphere cut in half. It is formed when a great circle is drawn. Okay, and the great circle is the largest circle that can be drawn in a sphere. That would be like, for example, the equator of the Earth. So right here, this is the great circle. And the reason it's called the great circle is because it's the biggest. If we took a cross section of the sphere up here, the circle that, like, if you could slice this hemisphere right there and look at it, this circle would be smaller than this circle, right? So the equator is the largest circle on the Earth that exists. So that's why it's called the Great Circle. So that's this. Yeah. That's what this is pointing to, the great circle. Okay, and it's really referring to the area of all of that, all right, being a circle. And then our hemispheres, half of our spheres, they still have a center, and they have a radius. So it has a diameter or a radius, and a center that is the great circle. All right, so the great circle and the hemisphere share the same center and the same radius. Okay, so some definitions and labeling for hemispheres. All right, let's take a look at our formulas and some examples. So starting with surface area, hopefully you watched the orange video and you saw the person trace the orange 4 times and then peel the orange and put the orange peel in those 4 circles. And that was to show you that any sphere, and orange is obviously not a perfect sphere, but if you can peel it away, it makes 4 circles. So the actual surface area of a sphere is 4 pi r squared. So 4 pi r squared, and r is obviously the radius of the sphere. Okay, so it's just 4 of them. If you've ever taken apart a baseball at the seams, you know that like it unfolds into 2 pieces. And if you look at those pieces, they kind of make like 2 circles that have been clumped together. And so you end up with those 2 pieces each having 2 circles. So then there's 4 circles total. Now, the surface area of a hemisphere. So obviously this part, so a sphere, it does not have any lateral area, by the way, because there's no base, right? So there's just total surface area. So that would also be the lateral area or whatever you want to call it, but it's just the total surface area of the sphere. So a hemisphere, though, it does have a lateral area because now it does have a base. And so it has the great circle as its base. And it still has a radius, right? And then this area, the area of the dome on the hemisphere, is just half of a sphere. Well, if a sphere had 4 circles, 4 pi r squareds, then the dome part, the lateral area of a hemisphere, would have 2. But then we have to actually add the area of the great circle, which is the base, which is 1 more pi r squared. So the total surface area of a hemisphere is 3 pi r squared. Okay, now if you're just looking for the lateral area, it's 2 pi r squared. All right, so half of the sphere. Okay, let's take a look at these. Find the surface area of each sphere or hemisphere. So total surface area of this sphere is 4 pi r squared, and r is 7. So 49 times, is that 196? Times 4 is 196 pi. And we are in feet. So our total surface area is 196 pi feet squared. For this one, we have a diameter. So our actual radius is only 11 feet. And our surface area is 4 pi times the square of our radius, which is 121 times 4, and that's 484 pi. So you can see these are pretty straightforward because there's only one variable in each formula. If we're finding the total surface area of our hemisphere, then we are going to do 3 pi radius squared. So 4.3 squared is equal to 18.49 times 3 pi is 55.57 pi. And that is in square feet. And remember, we can find the lateral area for a hemisphere too. So for good measure, we'll practice that. So that's 2 pi r squared. So 4.3 squared times 2, 36.98 pi square feet for a lateral area. And then our last one here, we have again a diameter. So half of 17.6 is 8.8 for our actual radius. So our total surface area is 3 pi times 8.8 squared, and that is 232.32 pi. And for our lateral area, we've got 2 pi times 8.8 squared. And let's see here. That is 154.88 pi feet squared. Oops, getting carried away with that arrow again. Okay, so surface area, lateral area. Again, spheres do not have lateral area, okay, because they don't have a base. Hemispheres can have a lateral area, which is just 2 pi r squared. Total surface area adds in that base, and that makes that 3 pi r squared. Okay, so volume. Volume does not get much more complicated, but we have a third degree. All right, the volume of a sphere is the space inside of it, and it is given by the formula of 4 pi r cubed, because we need that third dimension, divided by 3. So just like a pyramid or a cone, the volume gets divided by 3. So we have our radius as our variable. The volume of a hemisphere is going to be half of that. So 2 pi r cubed divided by 3. And you might see this as 2/3 pi r cubed. That's the same thing, right? Or this should say v. I paid for these notes. There's no excuse for that. Not like I don't make mistakes ever, right? All right. Like the beginning of yesterday's note, or whatever, Thursday's notes. Okay. All right, 4/3 pi r cubed. All right, so this is half of a sphere. Again, it has a radius, and that's our only variable. So that's it. We use these two formulas to calculate the volume of a sphere and a hemisphere. So let's see here. We'll do the volume of this is a sphere, so that would be 4/3 pi r cubed. And remember, order of operations, we do 13 cubed first, times 4 divided by 3, and so as an improper fraction, that is 8,788 pi over 3 cubic feet. And this one, we are given the diameter, so we need to cut that in half, and our radius is actually 9.1. So our volume is 4/3 pi times 9.1 cubed. Times 4 divided by 3. Okay, we're just going to round this one. Is 1,004.8 pi cubic feet. I haven't been rounding this lesson, but I did on that one because I got ugly. For our hemisphere, we have a volume of 2/3 pi r cubed. All right. Again, we're going to round. So the volume of this is about 219 pi feet cubed. And lastly, we have a hemisphere with a diameter. So our radius is 14.2. So our volume is equal to 2/3 times pi times 14.2 cubed. And times 2 divided by 3. We get about, I'm going to round again. It's going so strong. All right, 1,908.9 pi cubic feet. And that's it. That is our last lesson for this unit. All right, look for the review and study for that test. This is probably your last biggest chance to raise your grade, so make sure you are digging in. All right. Don't hold me to that. I don't know what's to come, but anyway. Okay. Bye. That's all for now. I'm going to stop before I'm too far behind. Yeah, that's it.